Hello, I'm Isabel Rayas Fernández, and I will be presenting our paper, Sampling-Based Motion Planning on Sequenced Manifolds, along with my co-authors Peter Englert, Ragesh Ramachandran, and Gaurav Sukhatme. Motion planning tasks in robotics often require planning with constrained motions, for example, when handing over objects between robots or keeping the gripper at a certain orientation. In this work, we address the problem of planning sequential robot motions in constrained configuration spaces. We propose an algorithm planning on sequenced manifolds, or PSM-star, which solves the problem of traversing a given sequence of manifolds for a certain class of sequential tasks by using sampling-based motion planning to grow a tree in configuration space. PSM-star is a probabilistically complete and asymptotically optimal algorithm. We begin by formulating the motion planning problem as a fixed sequence of intersecting manifolds M, which the robot needs to traverse in order to solve the task. Each manifold in the sequence implies a configuration space Cm that is specified as an equality constraint. The goal is to find a collision-free sequence of paths that traverses the manifold sequence while minimizing an objective function such as path length. The best overall path is selected subject to constraints that ensure continuity between subpaths, consistent changes in collision-free space defined by the operator epsilon, and subpaths that are collision-free and on the correct manifolds. We define the operator epsilon to describe the change in free space as the sequence of manifolds is traversed. In particular, a certain class of sequential tasks, which we call the intersection point independent problem class, can be defined for tasks where for each intersection, the output of epsilon is set equivalent for every possible path. In other words, the precise action taken to move the configuration from one constraint to the next does not affect the feasible planning space for the subsequent subtask. In this work, we only consider intersection point independent problems, which allows us to produce optimal plans with an efficient algorithm. The more general problem has been studied in previous work, and a discussion regarding related work can be found in the paper. Now I'll describe how the PSM-star algorithm works. PSM-star begins by initializing the tree with the start configuration of the robot, which is visualized on the blue manifold. The outer loop repeats for each manifold in the sequence. We use a routine similar to RRT-star to grow a tree from the current manifold to the next one, in this case, the green cylinder. In each iteration, the algorithm applies one of two possible extension steps. One is that a random point is sampled in the configuration space, and the nearest neighbor in the tree is extended towards it. The other uses a novel steering strategy that extends the tree toward the intersection with the next manifold. After the extension, we project the new point onto the current manifold. If the point is close to the next manifold, then it is also projected onto the intersection with the next manifold. We use the rewiring routine of RRT-star where we check for collisions and add the node to the tree. We store the points that lie on the intersection in a goal set. These points are represented here in pink. After the tree growing loop completes for one manifold, we initialize the tree with the found intersection nodes and their costs by adding them to a synthetic root node. Depending on the object manipulations that occur at the intersection, we update the free configuration space for the next subproblem and repeat. Finally, once the manifold sequence has been traversed and the goal manifold has been reached, PSM-star returns the optimal path across all manifolds. We evaluate PSM-star on several robot transportation tasks. Task A shows a basic pick-and-place task with a 6-stop robot arm. Task B uses 2 robot arms and 1 mobile robot to transport an object. And task C is a complex problem with 4 robot arms, a mobile base, and an additional constraint on each of the cylinders to stay in an upright orientation throughout the motion. We compare PSM-star to other methods, including CBI-RRT and random MMP. The results can be found in the paper. PSM-star solves these tasks consistently and with a high success rate. We also implemented PSM-star on a Panda robot arm. Here, the robot is able to complete both a simple pick-and-place task, as well as the more complex pick-and-pour task. In this work, we present 3 main contributions. First, a novel problem formulation for this problem using sequences of intersecting manifolds. Second, the intersection point independent problem class. And third, the probabilistically complete and asymptotically optimal algorithm PSM-star that solves this problem using a novel steering strategy. Our code can be found on GitHub. This work has many natural extensions. One that we have already begun to explore is how to learn a constraint manifold from demonstrations in order to use it within PSM-star for planning. Thank you.